Okay, we're gonna talk about a new data structure which will lead us into algorithms on graphs, which is a very, very big topic and will keep us busy for about 3 or 4 lectures or so. Okay. The reason that I think graph algorithms are really cool, besides the fact that they have tons and tons of applications, is because they force you, from a programmer's point of view, to really distinguish between some intuitive idea you have about how to do something and actually making that implementation work. And algorithms is about 2 things: clever ideas and getting that intuitive idea out of you and describing it. But once you've described it, there's still a ways to go in defining the data structures and the details of the implementation to make it work. And until you do that, you're still in vague land. And you have to at least make that some sort of a description, because it affects whether the thing actually works, and it affects certainly how fast the thing actually runs. Graphs are a super example of this, because it's just easy to think you have a method because we have visual cues looking at graphs, and forgetting that the computer doesn't have these visual cues at all. So in particular, here's an undirected graph, and somebody asks you, does it have a cycle? The question is so easy to answer that you're probably not even conscious that there's a method at all. In fact, I could put a big graph up on this board that's really large, and you could all, in seemingly constant time, glance at it and tell me yes or no, it has a cycle. So when I ask you to come up with an algorithm to find out whether a graph has a cycle, sometimes you just feel unable to do it because you don't even realize that there's anything that needs to be done. So the way to force yourself to realize that there is something that needs to be done is to slowly remind yourself that it doesn't look like this, and remind yourself of what the low-level tools really are for a machine that's going to do this problem. Okay, you're not in an AI lab, you're not developing eyes and all sorts of other things like that. You're looking at real-life specific algorithms. So we need to talk about how a graph's going to be stored. And there are 2 standard ways, and both those standard ways can be augmented with various features. And the 2 standard ways are very similar to each other. But one of the standard ways is a little more standard, and this is it. It's called adjacency lists. And it looks fancy, but it's not so fancy. Let's say this is called A, B, C, and D. Then what we would do is we would store the nodes in an array, 0, 1, 2, and 3. Say A, B, C, and D. That's just a little piece of data. And then after this piece of data, there would be a linked list. And in the linked list, we would list all the nodes that are adjacent to A, hence the name adjacency list. So in this list, we would list B and C. Notice we do not mimic the connectivity here with the pointers directly. We don't create objects that are nodes and point things back and forth from one object to another, mimicking exactly what we see in the board. That's not how it's done. And the reason for that is that it's not easy to implement, and it doesn't allow for really easy algorithms either. So the way we actually mimic this is a little bit different than just making pointers that look like these edges. We don't do that. Instead, we look at the things that are adjacent, and we just list them in a long list, B and C. Sorry, so B and C are actual indices. It would be 1 and 2. And B connects, what would be in this list? 0, 2, and 3. Let's quickly just finish this, make sure everybody gets it. In the C list would be 0, 1, and 3. At the end here, where I don't write anything, are little nils, right? These are linked lists, an array of linked lists. And in the D, we have B and C, which are 1 and 2, right?
Do we generally write them in numeric order, or does it not matter?
It doesn't matter. It's completely arbitrary. Although the order that we actually traverse this graph will be dependent on the order that it actually went into the data structure. But the order that it goes in the data structure is arbitrary. Sometimes you don't keep any names for the nodes. Sometimes you just refer to them by their index, so there wouldn't be an A, B, C, D, but usually you do. And sometimes there's other information that you'd keep in addition to A, B, and C, D, in addition to their names, information about the nodes. We'll talk about that very soon. The first example we're going to do is a motivation for augmenting this data structure a little bit to make algorithms work a little faster. But the primary thing that defines an adjacency list is an array for the nodes, some header information about each node, and then a linked list of all the other nodes that connect respectively to the node in that index. All right, questions? Yes.
If it were a directed graph, how would you restrict this?
It looks the same way in a directed graph. In an undirected graph, and that's a very good question, because I was just going to mention that. In an undirected graph, you should notice that every single edge is listed twice. Right? Does everyone notice that? For example, the edge from A to B, which is from 0 to 1, is listed once here. These values, even though they're nodes, really represent edges, right? So it's 0 to 1 and then 1 to 0. It's listed here also. So every edge is listed twice. So how many actual nodes will appear here? Twice as many as there are edges. 1, 2, 3, 4, 5. There should be 10. 3, 6, 8, 10. Okay? I just had a flashback to that count to 3 Monty Python scene. Anyway. All right, so look at this graph. Nah, it doesn't matter. Look at this graph. Does this graph have a cycle?
No.
The point is not whether the answer is necessarily yes or no, and I'm not sure if it is. We're going to draw this in a minute. But if I gave it to you this way, you have an answer. And if I give it to you this way and I say, make me an algorithm that figures it out, at least now you know what you're up against. Right? This is what the computer, quote, sees, whatever that means, and this is what you got to deal with. So does it have a cycle or doesn't have a cycle? If you're a human, your algorithm would be, go through this data structure and make a picture, then solve the problem. All right? You got to come up with a different way for the computer. So we're not going to solve this problem right now. In fact, it happens to be a problem on your problem set. But I'm going to teach you techniques that will help you solve problems like this. And we will solve a problem that's a little more elementary before we get into more general techniques. There are general techniques for traversing graphs. Breadth first search, depth first search. Those techniques, especially depth first, are basic tools that become the building blocks of other fancy algorithms. Finding a cycle can be done using a variant of depth first search. We're going to do examples that don't use these tools at the beginning, and then move our way slowly toward those tools and then build up a really, really cool algorithm using those tools. The coolest algorithm we'll do that uses depth first search is an algorithm that finds strongly connected components. That means if you have a directed graph, pieces of the graph where the nodes all connect one to another. So if it's a communications network, it identifies the parts of the network that everybody can communicate one to another. So if you start going down all over the network and you want to identify which parts can really still communicate all to one another, each part individually would be a strongly connected component. It's a very commonly done algorithm, and you want to be able to do it quickly. All right, questions so far? There's a lot of other algorithms that come up on graphs. Shortest path, minimum spanning tree. Those are famous ones, and we'll talk about them. And then some less famous ones. But here's a really cool one. If you make a picture of a graph, this graph, for example, and you'd like to know, is this a planar graph? Planar graphs are graphs that you can draw without crossing edges. Now, I happen to cross the edge here, but I could have drawn this graph without crossing the edge. Right? So the question is, given a graph, can you draw it without crossing any edges? That's a planar graph. Some algorithms run faster on planar graphs. It's important to identify planar graphs. For example, splitting a graph into 2 parts and getting the maximum number of edges that connect the 2 parts. It's called max cut. That's an NP-complete problem, which is polynomial time for planar graphs. There are a lot of problems that are better for planar graphs than for regular graphs, and it's important to be able to identify them quickly. How do you identify planar graphs? This is a really hard problem, but I'm going to give you a little review just because this is cool motivation. There's a famous theorem in math called Kuratowski's theorem, and it says this. It says that if a graph has, more or less it says this. If a graph has one of these, This is called a K5, a complete graph on 5 nodes. All the edges are there. This is called a K33. All the edges are between these 3 and these 3, but no other edges. If a graph is non-planar, then it has one of these inside it. And if it has one of these inside it, then it's not planar. In other words, all you have to do is look through the graph to look for one of those. More or less, that's what his theorem says. So you could figure out if a graph is planar by doing this brute force algorithm. Look at every collection of 6 nodes and see if they look like this. Look at every collection of 5 nodes and see if they look like that. How many groups of 6 nodes are there in a group of n? N choose 6. What's n choose 6, big theta-wise? Okay, it's n times n minus 1 times n minus 2, 6 times, and then with some number on the bottom. So it's order n to the 6. This is one slow algorithm. And it's actually a little tricky to implement. Because, like I said almost. Kuratowski's theorem says that either it has to be there, or if there are nodes that have 2 edges, you can collapse them and make them a single edge. So there's actually a little work you have to do even to get this to be order n to the 6. You like to do better. It turns out there's a depth-first search modification that finds out whether a graph is planar in time proportional to the nodes, in linear time. It's not obvious at all how to stare at this and figure out if there's a way to arrange the nodes on a blackboard so that none of the edges have to cross. It's just, I think, beyond hope at the beginning when you first start thinking about algorithms. But I want to give you an example of something that isn't trivial at all, isn't obvious, and there's a famous paper on this, and you can look it up and read it, and it's not so easy to do, but depth-first search is the basis of that paper, and it's a very useful algorithm. All right, questions about it? We're done with the intro now. Let's just label them 0. 0, 1, 2, 3, 4, 5, 6, 7. Okay, let's go through it, make pictures. 0 connects to 3 and 4, right? 1 connects to 2, 5, and 7. 2 connects to 1, 2, and 7. Did I write it right? I guess I did. I wonder if I meant this.
Next to 2?
Yeah, you can have a loop. I didn't probably mean that, but we'll put it in anyway. Now it's got a cycle. Yeah. D connects to 0 and 4. D. 3 connects to 0 and 4. There's a triangle. 4 connects to 0 and 3. We have that. F connects to 1, 2, and 7. That's 5. Connects to 1, 2, and 7. 6 connects to 2 and 7. And 7 connects to 1, 2, and 5. That should be there already. All right, so that's what it looks like. You can have loops in a graph. It's usually rare. Usually it doesn't mean anything to have a loop in a graph, but you can. Yeah?
Is this directed? It must be directed. It must be 6, but 2 doesn't go 6.
Generally speaking, we always assume the graph's directed, so all these edges I should have made, have directions. And the directions they go would be from 0 to 3, 0 to 4, etc.
Right.
So you should always assume that's true.
That's important when you're looking for a cycle, though.
Right. It's important when you're looking for a cycle. If I told you beforehand that this was undirected, then it would be completely symmetrical, and any edge I have from 0 to 3, there'd also be one from 3 to 0. So you don't have to be told in advance that it's directed or undirected. You just interpret it always as directed, and if it's undirected, there'll be 2 of those edges there, essentially. All right. Another question about graphs that's also obvious if you can stare at it is, what are the connected components? I'm not talking about strongly connected components. I'm talking about the underlying undirected graph. How many different pieces are there that are connected, and how many that are completely disconnected? So how many here? There's 2. There's a triangle, and there's this other thing that's sitting on top of it. Right? You don't get that at all from staring at this. Maybe you do. Maybe Michael does. All right. Well, it's certainly faster when you stare at it, at least for most mortals. Let's talk about an actual algorithm using this structure. Now before we do it, just very briefly, it should be clear, or you should even guess, that there's an alternative to this structure, which means instead of storing these things in linked lists, we'd have a two-dimensional array. And the number of columns here would be the same as the number of rows here. And instead of storing, the actual nodes that we're connected to, like 3 or 4, in column 3 we'd put a 1, and in column 4 we'd put a 1, and in all the other columns we'd put zeros. Everyone understand the difference? That's called the, the adjacency matrix or the incidence matrix. I don't know what the word is exactly. But it's just a different way of doing it. The difference tends to be that here, algorithms tend to run proportional to the number of edges, because traversing through this graph once basically looks at every edge at most twice, okay, if it's undirected. But if you have it the other way, then how long is your algorithm going to take to traverse through the graph? It's going to take n squared. So generally speaking, whether you use one data structure or the other has to do with whether your algorithm is going to be n squared or e. And generally speaking, e is going to be smaller than n squared for the most part. If you have a lot of edges, they're close.
E's the number of edges.
E's the number of edges, right. No, not the natural logarithm number, not 2.718, whatever.
Sure, you say in your notes order n plus e for the smaller case.
Right, because if there's actually fewer edges than vertices, we still have to look through this whole list. So it's really max n and e, but well, you'll see. How big can e get? How many edges can you have in a graph relative to n?
N minus 1.
No, it can,
N times n minus 1.
n times n minus 1 divided by 2, because you count each one twice. If it's a directed graph, then you can really have n times n minus 1. But altogether, it's about order n squared. Okay, so keep in mind that something proportional to the edges, when there's a lot of edges, is really the same as n squared for the most part. Edges is like n squared. Yeah. Okay, questions so far? Let's get to a real algorithm now. What is topological sorting? Here's the basic idea. What? Topla. Now it's topological. Since it's that never stopped us before. Okay. A topological sort of a graph only makes sense when the graph is directed. So we're talking about a directed graph. And intuitively, here's the way to think of it. Imagine that these nodes represent courses that you have to take, and that the arrows represent prerequisites. So this course needs to be taken before this course. So at ADU, a topological sort is very easy, right? Boom. There's nothing to do. A topological sort is an ordering of these vertices in a way that allows you to actually take those courses in that order. There may be more than one topological sort of a graph, just like there's more than one sequence of courses you can take in a big university that gets you through all those courses. You don't have to take them in a particular order. All right. So let's look at it. There's only one here, right? Let's give these names, A, B, C, D, E, F. And just make sure everybody gets the idea. So A would have to come first, right? And then what comes next? C would have to come next. And then B, and then D, then E, and finally F. In this example, there's no choice. There's only one way to take the sequence of courses, A, C, B, D, E, F, and that's it. If I erase this, then do I have a new way? Same. If I erase this, do I have a new way? Why not? I can take A, and then I can take B or C now. Right? It's okay. Now I can actually take D or C. So I could start with A, B, C. I could start with A, B, D. There's lots of orderings once I get rid of those prerequisites. There's lots of different ways to order these courses to be able to get through all of them, taking them one at a time. A, B, let's continue this one. A, B, C, followed by D, and then E and F. A, B, D, followed by C, E, and F. Well, I think those are the only ones.
So you can hop around wherever you want as long
as you've done the prerequisites. Right.
So why couldn't you do one of them in the first instance? Why couldn't you just jump back to C later on?
You could.
There's only one way to do it.
But you can't ever do E until you do C. So once you've done A, B, and D, you're kind of stuck going back to C to continue any place.
But you could have done it that way then.
I did. Here I did it that way. A, B, D, C, E, F. On the previous one, I had another choice that I didn't. That all right.
Yeah, you choice.
Just on the number of choice.
Perhaps I don't. Okay.
Right.
Okay. But everybody gets it. That's what I'm. All right. We might have missed one before. It's possible.
You actually did. You had that was the only way you could have done it.
Well, why couldn't you do A, B, D?
Because D requires C.
We used to have an edge
There
here
was an edge going from C to D.
at the beginning.
Oh, and B requires C.
Yeah.
Right.
So that was your.
No, at the very beginning, there was only one way. All right. Let's move on. Let's think about it, keeping in mind that there's an underlying data structure. Let's think about how we're going to actually solve this problem. And our goal is to do it as fast as possible. So we're going to do it in a way that won't be as fast as possible, and then we're going to fix it. And this is going to teach one really important concept in algorithms, and that's this. There is a trade-off between data structures and algorithms. The more fancy stuff you keep in your data structures, usually the less work your algorithms have to do. And the less fancy stuff you keep in your data structures, the more work your algorithm has to do. We are going to keep nothing extra in our data structure, and we're going to find that the first algorithm that comes to mind works a little slower than we'd like. But if we do just a little extra work at the beginning and make the data structure a little fancier, then the work that we have to do later on is a good deal less. So this trade-off between pre-processing and making your data structure more fundamentally functional makes the algorithms perhaps faster. And that trade-off is always there. So never think of an algorithm without a data structure. They all go together. Okay, who's got an idea? How are we going to topologically sort this graph? What do you do? Intuitively, how do you put it back to the data structure is the second part. But what's the idea first? Just intuitively on the picture. How do we do it? You all can do it. So how do you do it?
The node. We can only start at nodes that don't have any arrows pointing at them.
Right. You can only start at a node that doesn't have any arrows pointing at them. What if there were more than one? I mean, there could be, right? I can start at either one. Okay. So first step is let's find a node that has no arrows pointing into it. Why don't we find all of them? Find all the nodes that have no arrows going into them. All right, just because it's taken me a long time to write this, somebody invented the term in degree, which means how many arrows are going into something. So find all nodes that have in degree 0. Okay? Then what?
Pull that out of the graph and then do it again.
Pull it out of the graph means delete it, erase it.
Or put it over where you're sorting it and remove it from your graph.
All right, we'll deal with the details later. But I guess intuitively we're erasing it, we're pulling it away, and we're going to look at what's left. And there's going to be new nodes of in degree 0, and we'll repeat. So delete it, output it. By it, I mean the nodes. Okay, take it out of the graph, print it out, and then repeat until all the nodes are gone, until the graph is empty. Oh, that cold's coming on fast, huh? It's like a tidal wave. Okay, that's a very, very abstract algorithm. No details underneath, and we're going to have to talk about the details. While the graph isn't empty, find a node that has in degree 0, take it out of the graph, output it, repeat. Is it going to work? Well, it's kind of abstract, but...
Are we trying to find one way that this...
One way. I think it's okay. It looks okay to me. Maybe there's some subtleties we'll find out as we go down into the guts of the data structure, but the basic idea looks fine. I like this idea. Hey, what happens? Is this always guaranteed to finish? What if you get stuck? What if you can't find something within degree 0?
Then it's not a...
Then it's going to be in an infinite loop, right?
Then there's no way to take the last course.
Then there's no way. Okay. So you know what? You're all right, but you'd have to prove a theorem about that. You'd have to prove a theorem that says if the graph has any topological order, then this thing won't go on forever. And it's not too tough of a theorem, but it's intuitively just what you said. If there is an infinite loop here, if it goes on forever and can't find something of in degree 0, that can only happen if there's a cycle in this graph. If there's a cycle in a graph, there's never a topological ordering. Topological sorting works only on acyclic directed graphs, which are sometimes called DAGs, directed acyclic graphs. DAG, DAG.
Did you just check for that at the beginning? Before we started this?
It would be nice to know if it had a cycle before we started. What we can do is if we get to this stage and we can't find one, instead of just going on forever and keep trying, we can just exit and say you have a cycle. In fact, that's a good way of finding a cycle in a graph. Except that it doesn't tell us what the cycle is. So that's not perfect, but we don't even have to do it in front. We can just do it right here in the middle. Put a little if statement in there and get it out and say break. All right, well, fine, but this is much too abstract. We need to get very specific because now I'm going to ask you how long this takes. And to answer the question how long it takes, you're going to have to think about what's going on under the hood in the graph data structure. So let's try to do that. If we have to, we'll write the data structure down for this, but I'd rather not. I'd rather actually just keep it in your mind. Let's analyze how much each of these steps takes, assuming you have to do them on the data structure that's representing this. Let's think about it. Step 1, find all the nodes that have no arrows going into them. How are you going to do that? Maybe I should make a little picture. Let's do it. A points to B and C. B points to D. C points to E. Thank you. D is E and F. E points to F. F points to nothing. We're calling it DO for Donna. And DO points to B and C. Okay. Now you see what it really looks like. Looking at this, which nodes have in degree 0? How do you figure it out?
That don't show up in the list, in the linked lists.
The ones that aren't over here. Well, how do you do that? Unfortunately, the only thing we can do is look. Let's keep an array of all the nodes. We'll say we've seen you or we haven't seen you. We'll run through each of these linked lists one at a time. Every time we see a node, we'll put a 1 in that array that says we've seen you. And when we're all done, the slots that have 0 are the ones that have in degree 0. Agreed? That'll work. How long does that take? Not n. It takes more than n. You have to look through all the linked lists, and that's proportional to the number of edges. What's more, let's say that all the edges were connected to A, and none of these guys had any edges. Let's just say. Then, when you were done looking at all those edges, you'd have to then run through all these just to find out that there are no edges. So in the worst peculiar case, it's really e plus n. Okay, that's where you get the n plus e. So it's really both. This step, n plus e. Now we say delete it. Okay, well, we've got a list of them. We can go through that list and delete them one by one. How long is it going to take us to delete it? Let's take one that we want to delete, A. How do we delete A? Well, we certainly can just zero out, nil out this list. That's one thing. That's easy. That takes one step. We go to index A. We set it to nil. What else do we have to do? Right, we got to go through this whole structure again and
Nothing points to it. That's the whole point.
But index, if the integer is 0, then
We've already determined
it
what
would
this
appear
is.
anyway.
that's true. Do we have to do anything else then? Are we just done?
We're done.
I think we're done.
Completely done? Is it that easy?
The structure in the middle, we're lucky that A's right at the top, but never mind.
No, no. Are we lucky, or is it? Maybe that's all we have to do. Maybe we just have to make this nil. Maybe that's all that's involved in deleting it from the graph.
Oh, it means you will have to then check all of the ones. You're not getting rid of them. So you're going to have to keep checking the fact that that's an empty list every time you run through your nodes.
Well, it's still there. It's just nil. So let me cross it out. Now what we're going to do? Now we're going to go to D, or DO, sorry. DO, and cross out DO. Okay, so now that's crossed out. And now what do? That's all the ones of degree 0. Now we go back on our loop. We delete those two. We output them. A and D 0. We go back, and now we find all nodes that have no arrows going into them. So we go back through the structure again, and we do it all again. And there's no B and there's no C. All right. How long is this going to take? It's going to take,
For each node, basically.
the worst case, this step takes n plus e. We're doing it n times. So in the worst case, we get something like this. Now, it may not be that bad, right? How come it may not be that bad?
We get to delete all of the 0-degree nodes each time we go through it.
Right.
We have to go through it again.
Right, and when we go through each time, we don't go through all the edges each time. We go through only through the edges that weren't gone through the time before. But still, I could easily come up with an example that makes it worst case, where we get rid of one edge every time. So we go through all the edges, and then all the edges minus 1, and then all the edges minus 2. That's still, essentially a square function, not a linear function. So this is bad. N times n plus e is too slow. We want to do better. We want to be able to do this problem and go through every single edge a constant number of times, not n times. This is squared or even cubed if you think of e as n squared. We want to just make it order e. We want to get rid of that looping part. It's not that tricky to do it. We're just not thinking very efficiently here. So what part can we leverage here? And the hint is that we're going to do it by making our data structure a little better to start with. But we're still going to use the same idea. So same algorithm, different data structure, different implementation, different analysis. Yeah, Anthony.
Do you need to keep the data structure around if you want to find a different ordering? Because this comes up with one ordering, right?
Right. So if we delete it, we need to make a copy of it. Right, sure.
So,
Yeah.
Your
Yeah,
nodes
Tony.
keep track of the number of references to them, perhaps? Or when you link to a node, you comment it's linked to number or something along those lines?
Okay, that's a good idea.
Do one pass the array we make instead of just checking that it's connected or not connected, figure out how many times it's connected to, and every time we delete a node, take those pointers and decrement those by 1.
Like it's still the in and out degrees.
Everybody's coming up with more or less the same very good solution. That we can modify the indegrees of these vertices, not even touch the graph, and not have to recalculate the new indegrees of 0 every time if we modify as we go along. we'll do a calculation once at the very beginning. Here's what it looks like. What's the integree of all these vertices at the beginning? A is 0. B is
2.
How long does it take to do that calculation that I just did on the board? You go through this list, and instead of just marking whether you've seen something or not, same as we did before, this time you increment as you go. So every time you see B, instead of just saying, oh, I'm going to put a 1 in the slot for B, I'm going to add 1 in the slot for B. We do the same thing, except we increment instead of mark. So this step, calculating the integree in advance, a pre-calculation before the algorithm starts, and souping up our data structure ever so slightly by adding a field in each of the header nodes, all that takes is order E, or n plus E. But now that I've done that, I can look for the ones that have zeros. Here's one that has a 0. And I go through its list, B and C. And instead of actually deleting anything from the graph, I just go here to slot B and to slot C, and I subtract 1 from these two. And on the spot, if any of those turn to 0, I would look at their linked lists. Does that seem all right?
Wouldn't it be better to go all the way through?
Oh, it'd be actually crucial to go all the way through. Right. Right. If one of them turns to 0, you don't really want to go forward from that yet. But yeah, we should be a little more careful. And what order? I mean, which 0 should I pick first? So actually, in order to make this as easy as possible, so that you don't have to be going back and forth looking for zeros and forgetting where you were up to, the easiest way to do it, it's really natural, is to use another data structure, to use a queue. You do this calculation. You run through it, you look for zeros. Every time you see a 0, you throw that index A and DO on the queue. Queue goes this way. And now you begin a loop. Take something off the queue, look through its linked lists, and decrement the integree of everything that's on the linked list. So take off A and decrement B and C. They'll turn to 1 each. If any of them turn to zeros, what do you do with them? Stick them on the back of the queue, because sooner or later, when we get up to them, we want to delete them too, because they now have integree 0. So here's what it would look like. These would turn to 1s, and A would be gone. Now we do D0, or DO, and this comes off. It changes B and C to zeros. So this is gone, but now B and C are on the queue. So this is a perfect way to keep track of the one to do next. You just pull it off the queue. And if you ever get a new one that turns to 0, you put it on the back of the queue. You turn to integree 0, get online. Okay, you're going off. And that way you don't have to have any fancy pointers or crazy movements in your array. You keep it separate. You run things on the queue. The second the queue is empty and there's nothing on it, your algorithm's finished. This is a problem you'll have to do for homework. You have to actually code this. And it'll be a good problem to get used to working with graphs, because you're going to have enough of a little startup getting used to defining this structure with the lists and stuff. Yeah, Peter.
Set up order n plus e and not e.
Oh, because it's possible. Whoa. It's possible that if you're not paying attention, you just step on somebody's foot and you. It's possible that all the edges are here, and then you go through all of them, marking them in degree 1. And then you go here and find out that there's nothing. So in the worst case, you have to look at all the nodes after you've looked at all the edges. It's a technicality. Keep in mind, E is generally bigger than N. So saying order M plus E is just redundant. It's the same as order E. Are there questions about this algorithm? Yeah. Peter, you had a follow-up? Yeah.
No.
And are there any other questions about this? So it's a cool idea. You augment your graph data structure with the simplest thing possible, just an array of particular integers. You do a little pre-processing. That saves you a lot of work later on in your algorithm. It makes it more efficient. Now this algorithm runs in time. Let's figure it out. Order M plus E to set it up. And then every single node gets put on the queue exactly once. Right? Analyzing this isn't so obvious. Let's analyze it real carefully. Starting it up as n plus e. Every single node gets put on the queue once. So the actual putting things on queues and taking things off queues happen at most n times. Right? So that doesn't add too much. What else happens? Every time you take something off the queue, you decrement all the things in the list. When you're all done taking them all off the queue, this is not iteratively. Now you have to think of the whole picture at once. When you're done taking all these things off the queue and they've all come through, that means you have decremented every single one time for each edge that was in your list. And the total of those is E. That's a sum of E over the whole travel through the queue. It's true that each one, worst case, could go through all the edges, but they won't when you do them all together. Collectively, they will cover all the edges once and exactly once. So the worst case is going to be n plus e to set it up, n for the queue additions and deletions, and e for any of these decrements. So n plus e plus n plus e, it's all order e. So that's as fast as you can go. The depth first search example we'll do for this later on does the same complexity, order e. No better. Okay, questions about it? You guys get it? You ready to code it? Give me a couple days.
A couple more examples of the topological sorting rather than just courses prerequisites. How this structure comes up, this problem comes up.
Even in the nodes, like computer processing, what has to be done before.
Right, job scheduling. Yeah, like say you have an assembly line and this represents painting the car and this represents, putting the engine in. So this might represent the whole sequence of things that has to be done, and you want to linearize it in some sort of assembly line. So then the topological sort would represent what you can actually do in an assembly line.
As an example, it's like getting dressed in the morning.
Well, there's a practical one that's very challenging for something. That's true. You got to put your socks on before your shoes. Otherwise, you got your shoes on, you got your socks in your hand, and you go, duh. Well, look, that's true. Getting dressed in the morning is another example. Any scheduling thing is like that.
Any kind of parallel process, actually.
Which one needs to get done? Right, the constraints. For that matter, pipelining. This is important for pipelining. If you have an architecture, and these represent the different parts of the architecture, and that you can't get to this stage until that stage is finished, it gives you a sense of how many stages you can have in your pipeline. So it relates to a lot of things. It's not the only way to cut out a factor of n. There's another way that sometimes my students do. They say, hey, why don't we just reverse all the edges in the graph? And then you're worried about out degree. And it's easier to find out degree than in degree. Because then you just look and see if the thing's nil or not. If it's nil, then it's out degree 0. And if it's not nil, then it's not out degree 0. So that would be great as long as somebody gave you the graph with all the edges backwards. So then you say, okay, well, I'll just go in and pre-process the graph and turn it backwards. How long does that take? Well, actually, it doesn't take that long. It takes order e. You can do that. It's a good problem. I didn't put it on the test, but maybe I should. Go through a graph, make a new graph that has all the edges backwards. Right? You can do that proportional to the edges. So if you did that pre-processing, then your algorithm could change in a different way and still save the time. It's not the only way. There's lots of different ways to handle this problem. All right, questions, thoughts?
What does your shirt say?
It says, let me teach you a few tricks. What does it say in the back? Nothing? It's my bridge shirt.
I never get.
Duplicate after class. All right, new example. Minimum spanning tree is a really basic graph algorithm that requires a little more thought than the brute force method that we just applied. But I like the brute force method we just applied because we have to fix it a little slightly and make it a little better. So it's a good warm-up. But now we have to do something a little more. Nevertheless, I have to say that I really don't like this as one of the early graph algorithms to teach you because it gives you the impression that in algorithms, almost anything you try tends to work. And that's far from the truth. But that's what you get with minimum spanning tree. the first thing you think of works, and we spend most of our time talking about how to do it. Okay, what's the best implementation? And it's important because it's going to motivate a really cool data structure you've never seen, and it's going to give you a little review of heaps. So pedagogically, it's a nice review, but as far as the algorithm goes, you're going to go on thinking, hey, algorithms is just brute force stuff that you have to analyze really hard, and that's just math. That's not what it is. A lot of times you just have to think of the algorithm, like we did yesterday. It really is a creative process. All right, so minimum spanning tree. Let's explain the problem and do an example. Look out. Okay, here's a graph with weights on the edges. If you have weights on the edges, then in your graph data structure, instead of just remembering what you're connecting to, like I'm connecting to node C or node D, you also add an extra field that stores the weight. So it's just a matter of having, for example, if this is A, B, C, D, E, F, G, then A is going to connect to B, F, and G, B, F, and G. And inside here, you would store the weight 1, and here you'd store the weight 3, and here you'd store the weight 2. So your nodes in the graph just have an extra field in them that stores the weight. Okay? Excuse me, the things that represent edges have an extra field that stores the weight. It's not hard to store weighted graphs. A mild change in your data structure. Okay, so we can store this. Oh, I'm missing an edge on one here, right? I'll make it 1. So these represent distances or some kind of measurement for each edge between cities. And like I said the first day of class, somebody wipes out the city, there's a flood, and you want to reconnect the roads using as little asphalt as possible and let everybody get to everybody else, so nobody's isolated. And the best way to do that is without having any cycles, just to have a tree, and you want to do it with a minimum amount of asphalt, so the minimum weights when you add them all up. It turns out that the first thing you try works here, and it's such a basic idea that it's incredibly abstract. And when you try to implement it, you actually get 2 different ways to implement it that are so different that people actually attribute them to different people and call them different algorithms. And they really are, and they use completely different data structures. The 2 methods we'll talk about is one due to a guy named Prim and one due to Kruskal. Prim's algorithm and Kruskal's algorithm. There are other algorithms as well, but we'll talk about just these 2. They all have one thing in common. They're greedy algorithms. The first thing you try to do works in the sense that if we want to pave this city back together, let's pave the cheapest road first and go from there. And keep paving the cheapest road we can and go from there. And that works. And there's a theorem that proves that that works. What does it look like then? What should be what's an idea based on take the smallest edge you can and keep adding? Let's get a more specific idea. Let's actually do it, maybe. What should I start with?
Pick one of the weight 1 nodes.
One of the weight 1 edges. So which one do you want to pick? Doesn't matter, I guess. A, B. Okay, so here we go. I'll darken it. Now what?
Pick another one that connects something we don't already have.
Okay,
The
so...
algorithm, we'd have to do BF because that's the lowest weight.
We could do BF.
But FG could be, or GE.
Oh,
But-
they don't have to be connected?
Ooh, okay, so here's Mr. Prim and here's Mr. Kruskal. Okay? Prim insists that the next edge is connected to the tree you have started to grow. And Kruskal says, let this flower up lovely. He says, let it happen in parallel, disjoint trees, which is called a forest, and let the forests grow together. So Chris was suggesting we do it Kruskal's way, and Doug was suggesting we do it Prim's way, and they both work. So let's do Prim's first. If we're going to do Prim's way, then we have to go ahead now and pick the smallest edge, which is connected to the small tree that we've created, namely AB. Now, what are the candidates? 2, 1, 3, and 2. Right? Think about this, because when we implement this algorithm and talk about the details, we better have some data structure that has those numbers stored somewhere in a place where we can get the smallest one as fast as possible. Well, what does that suggest?
An object.
An object. What kind of object? Well, with heaps, we always have the biggest one coming out. We could have a heap that has the smallest one coming out. Then in one step, we can get that minimum value. All we have to do is be able to add new edges to that heap, because what happens when we pull this out of the heap and we add this? Suddenly the fringe has changed. We still have 2, 3, and 2. They stay on the heap, but we have to add new things to the heap. We have to add 3, 4, and 1. Hey, what about 3? Is that still in the heap?
Still there, but it's not there.
It shouldn't be there anymore, though, right? Because we better never choose 3. So we've got to be a little careful here. And actually, we're not going to keep edges on the heap. We're going to keep vertices on the heap. And we're going to keep the smallest edge from that vertex to the frontier. So the smallest edge from F to the frontier is 1. And the smallest one from A is 2. And the smallest one from B is 2. And we'll take the smallest of all those. So we won't keep edges on the heap. We'll keep nodes on the heap that represent our frontier. And we'll keep them ordered by the smallest edge coming out of them. We'll talk about these details in a little bit. I'm just giving you a little preview. Let's just make sure we can finish this algorithm, then I'll come back and do these details in much more specifically. Specific. You know what I mean. There's a word there. What comes next? This one. And then GE. GE. We got a 2. We also have this 2, right? This 2 better not be a candidate. We have to make sure that in our algorithm, this edge is not ever considered. The reason it wouldn't be, well, is because what are the nodes now that are on the fringe? A, B, F, G, E. These are all on the fringe, right?
A isn't on the fringe anymore, neither is G.
These guys only connect to things themselves. How are we going to store that in our data structure? How are we going to know that we should never pick this one? You'll see. We're going to have to be careful about that. But I'm pointing out possible pitfalls. That we can do it with our eyes, but it might not be so easy to do in an algorithm. Well, it will be, but we have to think about it. So the next one is 2. And now what's left? Either of these is OK. Let's pick this. And then we're done. The town is saved, right. If we had done Kruskal's algorithm, we would come up with the exact same tree, but it would grow in a mildly different way. So I'll do it with a different color. Let's do Kruskal's algorithm. Let's start with the same thing. And now we go here. And then we go to the other one, say here. And now we connect this one. And now we got to go to the 2s.
Need to connect that one?
Yeah, because it's
connected to F.
But we're not connected, the 2 aren't connected together. And they need to be eventually.
it doesn't make a cycle to connect these two. And since it's the smallest available, we have to use it. So the next one that's the smallest available that doesn't make a cycle is this 2. So this comes into play. And finally, one of the 3s. So let's pick the same one. So it grows in a slightly different way, but it gives you the same tree. There might be more than one minimum spanning tree if you have the same weight for 2 trees. That's possible. Bless you. Questions about this? Yes?
Does it
Joe?
always give you the same tree?
Unless they have 2 of the same weight, it would always give you the same tree. Yeah. I mean, in this case, you could have DE instead of FD, and that would be different because you have 2 of the same weight. So the answer is generally no. It doesn't have to give you the same spanning tree unless there's a unique one with that weight.
You get your spanning tree of the same weight.
It will always give you the spanning tree of the same weight, right. Kruskal's and Prim will always give you the same answer. The minimum spanning tree has weight, 20 or whatever. All right, other questions? We have to talk really carefully about how to implement this. It may not be obvious.
If
If they're all ones, does it give you the minimum?
If they're all ones, then the minimum spanning tree is always going to be n minus 1, right?
No.
If they're all ones,
The sum of the minimum spanning, it depends on the topography of the graph.
no, I don't think it does.
Sure, if all of these were ones, we would still only want to color 5 through 5 of the lines, not even though we had 10 edges. Okay.
N being nodes.
Oh,
And other nodes, right? We have to have every node connected to the graph, and every time you connect, yeah. I think the minimum spanning tree problem isn't interesting if all the edges are just 1. It's just the answer. You just say n minus 1, and that's the answer, where n is a number of nodes. And there's a gazillion trees that give you that weight. There's 4 to the n spanning. Remember how many spanning trees there were? Here's the dopey way of doing minimum spanning tree. Go study Catalan numbers really carefully. Convince yourself that the number of spanning trees is the Catalan numbers of the graph, and that means that it's about 4 to the n. Remember we proved that 4 to the n the last day of the discrete math thing. It's a huge number. And then go through every one of those spanning trees and calculate which one has the minimum weight. So that's about 4 to the n time. Horrible algorithm, especially when you can do it this fast. So our goal is to get this algorithm to work as fast as possible, and let's see how we can do it. Let's make some data structures. We're going to have 2 arrays and a heap. The 2 arrays are for basically the value helps you keep track of the values of the things in the heap, and the parent array helps you keep track of the spanning tree that you've discovered so far. The parent array is a way of actually storing a tree. In this example, when we went from A to B at the beginning, that would set the parent of B to A, basically storing this edge. When we then went from B to F, that would set the parent of F to B. Right? So the parent array is an array that really is going to represent a tree, simply by storing parents. No left node, no right node, just back parents. If we fill this up, we'll have exactly what the spanning tree actually is, and that's going to be our goal. I'm going to do this very specifically in an example. So let me put a big example up on the board. And then I'll show you where the heap comes in, and we'll talk about the algorithm. Uh-oh. Maybe it's too big, huh? You'll probably get this before we're done. That's it. There's 12. I got to put edge weights on this graph. So here they are. 1, 1, 2, 3, 4, 3, 4, 5, 2, 2, 2, 2, 3, 5, 3, 4, 2, 4, 1, 4, 6, 3. All right. That's the example we're going to use. Can you see it? Not really, huh? No good. Too dark, too small, too... Can you see it? Who can see it? Nobody. EJ, can you see it? Yeah, all right. Eagle eyes. All right, let's talk about how this is going to work. The way Prim's algorithm actually works is that it doesn't necessarily start from the smallest edge. It just picks a node at which to start, and it uses the smallest edge from that node. That doesn't have to be the smallest edge overall. So it just picks a node that it's going to call the root. And it can do that arbitrarily. It can just pick the first one in the array in the graph. Just pick the first index. So think of this as the root. And the way it does this is it says, let me write these down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here are the array indices. It sets the parent of this to nil. That means that that's the root. That's where we're starting. And the value of this is 0. That means that this is in our spanning tree so far. It's the only node that's in our spanning tree so far. It costs nothing to connect this to the spanning tree. It's already there. What you do then is, in order to be able to continue, you're going to need to have the smallest edge that's connected to this in order to decide how to go forward. You need to connect the fringe. So in order to figure out what the fringe is, we're going to move forward by looking at all the things adjacent to 1 and looking at the edges connected to those things, which is 1, 3, and 4, and setting the values of those nodes to 1, 3, and 4, saying it will cost you 1 to include this in the new spanning tree. It will cost you 3 to include this, and it will cost you 4 to include this. Value is the cost that it takes to add that new node into the spanning tree. Everybody get what value is? So basically what we want to do is pick the value that is smallest, and that's the node that will come in. And we want to make sure that we keep these values updated carefully. So what should these be initialized to? 0?
-1 or something.
If they're 0, then they need to be a really big number at the beginning. Because the idea is, these are going to be heading down, down, down. Well, you'll see. The idea is they change, but they always get lower. So if you're going to initialize these at all, they should change. They should be initialized to infinity, or to something very big. So I'm going to write this down. They're all going to change as we move. In other words, right now, before we have looked at any edges, it costs an infinite amount to connect any of these nodes into the subtree. As far as we know right now, there are no edges connecting out there. The minute we look at these edges, 1, 3, and 4, we're now going to change. The value of 2 changes to 1. The value of 3 changes to 3. And the value of 9 changes to 4. All right, let me stop here and make sure everybody gets it so far. Everybody gets what minimum spanning tree algorithm is, and then you start talking about the implementation. It's like, ugh. So let's make sure you get it. Prim's algorithm keeps an array of the value. That is, how much does it cost to get this node into the spanning tree? Okay? The parent is, if this node were in the spanning tree, how does it connect back? So the parent of the root is nil. If we were to connect 2 via this edge, then what would its parent be? And this one would also have 1. So we're going to take all these values and set them to 1. 9 is 1, 3 is 1, 2 is 1. That means that if we were to bring these in, then they connect back through the tree. So the tree kind of looks like this now. But this is not going to be the spanning tree. This represents the fringe, and we're going to choose one of these to actually be connected. Okay, questions so far?
What did the parents set to initially?
The parents are all undefined. I guess they could be nils for now.
Could they be?
Yeah.
I thought the first one is nil.
But they'll all get changed. They'll all get changed. So even if they were nil, they'll get changed. Here we actually have to have big numbers because we're going to do a comparison, as you'll see later. Otherwise, 0 would have worked out. So. Okay, questions so far?
So you're actually putting the number 1 in this array for each of those?
Yes. Let's move on and see what happens next. And see if we can make what happens here in the picture happen here. What will we normally do next?
Pick the lowest one.
Pick the lowest one of these values, right? So when we set these values, where are they also going? They're going to go into a heap. Here it is. A min heap. A heap that keeps the minimum on the top. Okay? They all go in there. And they're all there right now, including the ones with the infinite values. You put them in the heap right at the beginning. They're all sitting in a heap. This just keeps track of their values. But we're going to fix this heap anytime a value changes to maintain it being a heap. So there's a heap of all the nodes at the beginning. There's only one guy that's not in the heap right now. Which is the one that's not in the heap at the very beginning? Right, the very first one's not in the heap. The only things that are in the heap is the candidates for the next node.
Does it make sense to have the heap contain all the nodes?
At the beginning.
Isn't that just adding additional overhead? Couldn't we just build
Add them in as you go?
Yeah.
You could, and different algorithms do different things. But we're going to assume that we just build it at the beginning and they're all equal, and then we modify it as we go. But some algorithms put them in one at a time. I think our book builds it all at once, so that's why I'm doing it this way. But you could do it that way. That's true. All right, so at the beginning, there's all the nodes except one, except the node 1, which is out. And as we go ahead and add new nodes to the spanning tree, we're going to take them off this heap. So step 1, go to the heap, find the minimum value, add that node to the spanning tree. OK. Let's do it. What happens? Let's list all the nodes here. So they were 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 is now off the heap. OK?
So the heap contains both the value and...
The heap is ordered by these values, but it stores the names of the nodes themselves. That's normal, that a heap has data values along with a field that you do the ordering on.
Sure. But it's edges that connect at it.
Say that again?
You put the edges that connect at a 2 into the set those values.
Right. We have to. Right. Good. Next point. So let me cross this out because it's out. Now this one's out. What else changes?
The value.
Andrew was talking about. What else changes?
We have to add a new node.
This is now in the spanning tree. Can we just go on now and get the next smallest?
We have to add the ones that
We have to look at 2, see the edges that it connects to, right? And update our value and our parent. We have to extend the fringe. How is it going to extend the fringe? 4 is going to have the value 1. Did 4 have anything before? 4 had infinity before, so 1's better. Let's make it 1. 3 used to have 3. You see how 3 used to have a value of 3? What's the value now?
2.
It changes. That's very important. We used to be able to get to 3 through a path of 3, and that was low on the priority queue, but now it's moved up because we can get to it through a faster node. So we have to keep track of that, and this now changes to a 2. Get it?
We're also changing our parent as we do this.
That means the parent of 3 is no longer 1. The parent of 3 is now 2. 4, the parent is also 2. What were the parents before of these? They were all... No, they should have been... No, the parent of 3 should have been 1. How come I didn't write that down? Oh, I erased it. I want to leave it there and just cross it out. And the parent of 4 was nothing, and the parent of 9 didn't get changed. All right, so keep in mind, I need to explain again. This parent structure right now does not represent the current spanning tree. It represents the current potential fringe. In the end, it will represent the spanning tree when those fringes all go away. But right now, we don't mean to say, now it looks like this. We don't mean to say that these edges are going to remain. They may change. These parent things may change. When we're all done, they'll be right. But right now, they're in their amorphous state. Let's keep going, make sure everybody gets this. I'm sure you don't the first time you see it, so let me make sure. What's next step? Now that we've modified the values and modified the pointers, the parent pointers. We need to go back to the heap and get the next smallest edge that's connected to the fringe. What's connected to the fringe? We've done this and this now. Is that right? So what's...
we're pulling 4 off now, and then we're going to connect.
Look through this list. We get 2, 1, 4. 1 is the smallest. If 1's the smallest, what happens with 4? Goodbye. Delete it from the heap. 4's gone. I'll cross that out.
So you've got the values in an array and an additional heap that's keeping the nodes, keeping track of those?
The heap is stored as an array. So you can think of value as the heap, except I want to remind you that there's also these extra data fields so that you know which node you're talking about.
So what data structure are you using?
The heap is represented by an array like it normally is. And inside it are slots. And in each slot is held a value and a node and a name.
You can't find the nodes very fast.
No, sure you can. They're right there. If you want to find the smallest one and you look up 1 and you pull it out, then a bracket value will be 1, and a dot value will be 1, and a dot name will be 4.
You had to change 4 to 1. Right? It was infinity, and then you set it to 1.
Right.
But then you got to go find that heap, find the node 4, and that's not key down. That's just the key's organized on the heap's organized on the value. Yeah. It's not organized.
Oh, you're right. We have to.
So you don't know where that 4 is.
You're right. You're right, Neil. That's an excellent question that I didn't understand at first. You're right. We need to be able to get from the value to the place in the heap that has that value. So we need to have this kind of inverted index, like you had for one of those problem sets in the last one. It's a detail that I really should talk about, but it's going to mess up the whole flow here, and it's an important detail. You got to be able to get this value and find that value in the heap, and it's not hard to do that. You just have to keep a backwards index of the array, and it's important to do. You're right. You're right. Yeah, Doug?
Actually, I kind of answered my question. I was going to say, for the 4, it's not an issue because that's the one that's on the top of the heap, so we know where that is. But when it comes time to change the parent of the thing,
right,
we need to have an easy
and we're going to do that right now. We're on 4 here. We're going to look through all the edges connected to 4, and we're going to change values.
Because it's the one.
So let's go around. Let me make sure.
It's an inverse.
We're looking at 4. We're going through 4 to extend the fringe. The fringe is going to get extended here, 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 and here. So let's see if anything changes. Does the value of 5 change? It does. It was infinity, and now it's 5, and the parent is 4. How about 6? 3 and the parent is 4. How about 7? 3 and the parent is 4. How about 3? It's already 2. That value is 2, so we don't need to change it, and we're not going to change its parent. We only change it if it makes it better. Okay? That way we keep track of the appropriate, best way to get each node that's on the fringe. There's got to be an array that tells you where in the heap index 6 is. You find it, you change its value, you fix the heap. That's what Neil was talking about. It's a very good point. Once you've done that, the heap is now fixed. What got out of the heap now? 4 is out, 2 is out, 1 is out from the beginning. Now we have to go through our heap and find the smallest one. No, there's a 2 someplace, right?
Yeah, the value.
Oh, this one. So now we're going to add this one in. Where do we add it to? How do we know that? Right. That's why we've been keeping track of the parent. The parent are the potential places where when we connect these nodes, that's where it's going to be connected. And it's always pointing to the smallest way to connect that node to the fringe. It's perfect. And now that we've made this part of the tree, how do we distinguish a parent pointer that's there potentially and one that's part of the tree? We distinguish it because now this is off the heap, and therefore we will never ever change that. All right. What's next? We got to go forward from 3 and see if we change any of the others. Notice 3 connects to some things that are already off the heap. Right, we don't look at those at all. You just look at the ones that are still in the heap. So maybe
How are we going to know they're off the heap?
you could have a little array that says in heap, off heap, like in queue, off queue. And that's easy to maintain as you go. If you delete something off, you change it from 0 to 1. So that's also something you can do. There's other ways to do it, but that's brute force pretty easy and doesn't cost much. So you can keep track of what's in the heap, what's not. So 3, we're going to look at 4, 6, 7, 8. Not 4, and not 6. Just 7 and 8. So what changes? 7 turns to a 2, and the parent becomes 3. And then 8, 3, and 3. And now we look through this list and we find the smallest. What's the smallest? That one. A weight of 2, edge vertex 7. That means we're going to include this. That means 7 comes off the heap, and now we have to modify. Let's keep going a little bit more until everybody gets it. See, about a third of you get it so far, but we're almost done. 7 is going to hit 6, 11, 10, and 8.
6, 11, 6, 11.
Oh, jeez. 6, 11, and 8. All right, so if it goes to 6, 6 is already 3. We don't change that. Going to 11, that's 4. 11's infinity. Parent is 7. So everybody see why we initialize these to infinity? It's so that when we ever hit them at all, we know it's better that we can get to them with some weight than what we knew before that we couldn't get to them at all. Because it is possible that this is disconnected, in which case you'd never get those nodes.
So Shai, you actually have another data structure, right, for this graph?
You have something that's storing this graph so that when we get to node 7, we can actually look through the list and go through it. Yeah, absolutely. You got a lot of data structures. You got arrays, you got a heap, and you got these auxiliary arrays that help you find whether something's in the heap and how to go back. Yeah, there's a lot of stuff here.
That's a practical issue. We don't really have infinity as a value.
You
just do something.
in most languages have like max int, some big integer. Just use the biggest integer you have. Yeah.
It just has to be bigger than the biggest weight.
It's got to be bigger than the biggest weight. That's all. You can set that as a constant somewhere in your program. Let's go a little more forward. Did I do all these yet? What about 8? 8 doesn't have to get updated? Oh, it goes to 2. Okay, so this, thank you. This changes to 2, and this changes to 7. All right, let's continue. Now look at it, and the smallest one is number 8, so it goes this way. This gets knocked off. We go forward from 8. I'm going to get it right this time to 9 and 10. 9 doesn't get changed. 10 should get changed to 2, and the parent is 8. We look through the list, and we find that the next one is 10. That gets off the heap. We go this way. We go forward from 10 to 9. It doesn't change. To 11, it does change. This becomes 3, and this becomes 10. And then we look through our list, and we have 3s. We can pick either one. Let's do this one. Let's assume just randomly that it did this one. So this is now off. I haven't been doing it. Okay, that means we are adding this edge, right? The pointer back to 4. And now we're going to go forward from 6 to 5 and 11. And which one is going to change? They both change, right? 5 changes to 4, and the parent of 6. And 11 changes to 1, and a parent of 6. All right. Let's stop for a second. We're almost done with this example, but I want to, everybody's been bringing up lots of questions, and one of them came up that we said we could do with an extra array, but maybe now you're able to hear the complete answer. I think this was Mike's question. The question was, how do you know not to check the ones that are already in the heap, that are already out of the heap? Like when you're doing 6, we're going forward to 11, and we're going forward to 5. What if we check 4? What would happen if we checked it?
Nothing, it'd just be a waste of time.
It would just be a waste of time. You're never going to find a better way to get back to 4 doing this algorithm. The whole idea of this algorithm is the greedy approach. And the theorem behind it says that if you ever have to go back to 4 later, it's always going to be by a bigger edge, because you'll always pick the smallest so far. So if we did do it, Michael, we never ever have to change it or get an error. It just would be a waste of time. So it's a question of efficiency. Is it worth to look at an array and say, no, I don't want to look at this? Or do you just go ahead and look at it and let the if statement, come out and say, I'm not doing anything? Most of the time, we don't bother putting it in an array and then checking first to see whether we want to look at it. We just go ahead and look at it and have it do nothing. Okay, so usually you won't see that array in the normal implementation. Does that make sense? It's a good question.
Actually, just to
yes,
make sure
Doug?
I'm clear on that. Suppose, for example, that between 5 and 12, it's only 2. Suppose we'd gotten to the 11, but not to the 6, so we didn't, had it seen the 2 between the 5 and the 12.
That's going to happen right now, actually, because the next smallest is 11. Right? We're going to do this next. And 11 comes off.
And then we, suppose we did the 11 to 12, which, just go ahead, maybe I'll...
Maybe you'll see it happen? Okay.
The question.
So now we're going to go forward from 11. None of these change. Right? The 4 is worse than the 2. The 3 is worse than the 2. You expect that, because these are already connected as good as they're going to get. They're already in the tree. We're never going to look back. Don't look back. That's what this theorem says. But we will look forward to this 4, and that makes 12, 4, and the parent is going to be 11. Now what? Let's look through our list. We've got a 4, a 4, and a 4. Any one is OK. Which do you want to do? 5 to 6, we'll do this one. That's fine. That means we're taking out 5. We go forward on 5, and it does change the value of 12 to 2 with a parent of 5. And now we look back, and now our list is a 2 and a 4. So we do the 2 first. Now that one's out. There's only 1 left. It's kind of easy to delete a heap that has 1 element in it. You don't have to find the minimum. It's just the only one left. So you pull it out, and you're done. When the heap's empty, the algorithm stops. Right. This is the normal way to implement Prim's algorithm fancy. There's actually a less fancy way that uses a 2-dimensional array rather than a adjacency list. But this uses adjacency lists and a heap. And before I quit, I want to analyze this with you. And then we'll quit at the end. We'll do Kruskal's next time. Kruskal uses a different data structure completely. No heap, none of this hard stuff. It's much more intuitive. And the result in Kruskal's algorithm is really cool. I'll mention it before we quit today. And the math is real hairy. So like we've always done this semester, we'll do the cool result and we'll leave the math for some other time.
They both have the same order. These 2.
They both will have the same order. No. Kruskal with a hairy amortized analysis is a little better. And I'll tell you what that is before we leave. All right. Now that we've done that big algorithm.
Could you actually connect the 1 to the 9? So that we actually
Oh yeah, I pulled the last one out. Where did I pull the last one out? It's number 9. And that goes with this pointer, which has never changed from the very beginning. More than aesthetics. Now we're cooking. Yes. And there's the tree.
not very spiritual.
Yeah, it's the elephant man. There's the eye. There's the trunk. Let's. All right. All right. All right. Take a breath. it's a little painful to see an example this long, but if you were really having trouble getting the idea, this is the foolproof way to make sure you get it. So I like to do these. I think they're worthwhile. But now we're done. So let's relax a minute and analyze what we've done. Analyze how long it took.
That sounds relaxing.
Let's remind ourselves what happened in this algorithm. We started out making a heap of all the nodes except the root. How long does it take to build a heap? It takes n. All right, so that's n for building the heap. That won't cost us much because our overall complexity is going to be worse than this. What did we do next? We went through, we deleted from the heap, and what did we do every time we deleted from the heap? We went forward along the edges connected to that heap, and we asked an if statement question. Is the weight on this edge bigger than the current value? And if it is, don't do anything, but if it's smaller than the current value, then change the current value and change the parent. Okay, there's a constant if statement question for every edge connected to the node that we just took off the heap. So let's try to analyze how long this takes in the worst case. How many of those if statements are we going to ask total? All the nodes will eventually get knocked off the heap. How many of those if statements do we ask? Proportional to the edges. Every one of them has a bunch of edges connected to it. If you take all of them collectively, it will get all the edges connected in the whole graph. We're going to ask that if statement, at worst, for every edge in the graph. Right? Okay. How many times do we take something off the heap? Proportional to the nodes. So we ask the if statement at most e times. We take something off the heap at most n times. How long does it take to take something off a heap? You have to take it off in constant time and log n to fix it. So since we're taking n things off the heap, n log n, the total of all the if statements is e. How long does it take to ask that if statement and do the right thing if you have to? Be really careful when you answer that question. Let's go over the if statement again. At any point along the way, let's say this last one, we're going to check if the edge from 5 to 12 is smaller than the current value of 12, which at that time was 4. And the answer was yes, it's smaller. Well, that takes one step to ask that question. You compare the edge weight, which is in your data structure, with your value, which is your array. That's a constant time question. If the answer is yes, what do you have to change? You have to change this value to 2, and you have to change the parent to 5. Changing the parent is easy. That's one step. Changing the value is easy. That's one step. I got to maintain my heap when I change the value. Every time you change the value, you have to go back to the heap and fix it. Here's a heap full of stuff with people with priorities in it, and you just change somebody's priority. Vertex 12, which used to be kind of low on the priority scheme, just moved up. You have to change the heap because vertex 12 better move to the top. That means for every one of your E questions, the worst thing that might happen is you might have to fix your heap. So it's n plus n log n plus E log n. And which one of these is the worst? E log n is the worst, and that's the complexity of Prim's algorithm, done in this way, E times log n. Let me just say something. I could have spared you a lot of pain. No heap, no adjacency lists, just a two-dimensional array. And then, as you're looking through the edges that are connected, you have to look through all n. So instead of it being E, it ends up being n times n squared, to go through all the edges. And as long as you're doing that every time, you might as well calculate the minimum with a linear time algorithm, because you're not losing anything. Because if you calculate the minimum n times, that's still n squared. So if we had used a two-dimensional array, we could have had an n squared algorithm for Prim, because we wouldn't have used a heap. We would have just calculated the minimum from scratch every single time we added a new node. It would be n times n. We didn't do that here because we didn't want to make it E times n. That would have been terrible. So we used the heap here. But if you're going to use a two-dimensional thing where you're already up to n squared, it doesn't hurt to do linear time at each iteration. How do you compare n squared the two-dimensional array version, to linked lists and heaps of E log n. Which is better, n squared or E log n?
Is E proportional to n squared?
Depends on E. I mean, E in the worst
It is in the worst case, Neil, right. So in a really bushy graph with lots of edges, this is about n squared, and n squared log n is going to be worse than n squared. But what if it's a very kind of a sparse graph with very few edges? What's the best the graph could have if it's connected is just n edges? Then that would be n log n. So for very, very, very sparse graphs, this is definitely better. And for bushy graphs, this is better. They are both used. This method is really, really nothing as fancy as this. The values are kept in an array, no heap. You calculate the minimum from scratch by just looking through your list of values every single time through. There's nothing fancy about it. No modifying the heap at every stage. So this stage doesn't exist. This stage ends up being n, and this stage doesn't exist. So it's just n times n, n squared. All right, those are the two ways to do Prim's algorithm, and which one is better depends on the number of edges. A brief note before we quit about Kruskal's algorithm. Kruskal's algorithm is the one that generates these forests and has them go together. The data structure is really cool. You've never seen it before. It's a nice segue from graph algorithms, from data structures to graph algorithms. We'll talk about it tomorrow. It's also a connection to amortized analysis. If you analyze how long it takes to use this data structure on Kruskal's algorithm, it turns out that over the long run, doing lots and lots of unions and connecting these forests together, even though the worst case of connecting two of these disjoint trees might be bad, but overall doing lots of them, the average one turns out to be very small. And here's what the complexity turns out to be. It turns out to be big theta E times, I'll call it really small, really small times n.